Hi, everyone. Let's take a look at this Chapter 13 worksheet. Chapter 13 is on nuclear magnetic resonance spectroscopy, both proton NMR and carbon NMR. So the first set of problems on the worksheet are for carbon NMR, and then we have some practice questions on proton NMR, and finally we have a practice question with a combination spectroscopy problem, which will also be fair game for the first exam. So this question has a very similar format to that infrared question that we saw on the Chapter 12 worksheet, in which we're given 6 structures and 4 spectra. And what we need to do is match each spectrum to the correct structure based on the chemical shifts, based on the number of chemically distinct types of carbon that are available, and we don't have integration or spin-spin splitting in carbon NMR, so that's pretty much all we have to go on. And in carbon NMR, that's generally sufficient. This is why carbon NMR spectra and interpreting them are very much simpler than for proton NMR spectra. There's just less going on. There's no spin-spin splitting, and there's no peak integration. So, for example, let's take a look at spectrum A. There are 4 peaks. We're given a little indication here. This sort of looks a little questionable here, this peak over here, but it says there's only 1 peak here at 61 parts per million, not 2 peaks. So there's a total of 4 peaks. That means there's 4 chemically distinct types of carbon. So we're looking for a compound that has 4 types of carbon. Well, let's count all the types of carbon in all of these. Let's look at compound O first. There's 1 type of carbon here attached to the OH. Then we move out 1 carbon. Those 2 CH2s are equivalent, so that's another type of carbon. And then that unique CH2 out there is different from these CH2s because it's a different distance from the OH group. So 1, 2, 3. There's only 3 types of carbon in compound O. Can't be that one. Compound R is cyclopentane. All the CH2s are the same. So it can't be that one either. That would have only 1 peak. As for compound P, the 2 vinylic carbons are the same. Those 2 CH2s are the same. That's another one. So we're up to 2. And then this unique CH2 here is a 3rd type of carbon. So there's 3 types of carbon in compound P. Can't be compound P either. In compound S, these 2 carbons are the same. Also, those 2 carbons are the same. That's a 2nd type. So there's 2 different types of vinylic carbon. We'd expect there to be 2 different peaks in the vinylic range for this compound. And then that CH2 is unique. So there's 3 types of carbon in compound S as well. So it can't be O, P, R, or S. What about Q and T? Q has 4 carbons in it, and they're all different, aren't they? This CH2 is connected to the OH. This one is not. This carbon is vinylic and there's a hydrogen attached. This carbon's vinylic and there's 2 hydrogens attached. So they're all 4 different. So indeed, we would expect 4 peaks for compound Q. What about compound T? Well, same thing. There's 4 carbons in it, and they're all different. There's the carbonyl. There's the CH2 directly attached to the carbonyl. There's this CH2, which is 1 carbon further away from the carbonyl, and there's the CH3. All 4 of them are different. So again, we would expect 4 peaks for compound T and 4 peaks for compound Q. So how do you know which one this is? The way you know is by looking at the chemical shifts. If we had compound T, then we would have an aldehyde carbon, that carbonyl carbon. Carbonyl carbons are very far downfield, especially for aldehydes and ketones. For esters and carboxylic acids, not quite so far downfield. They're at maybe 170 parts per million. But aldehyde and ketone carbonyls are at closer to 200 parts per million. There's nothing there. There is no carbonyl carbon. So it must be compound Q. Just let me double check that before I get too far ahead. Let's see. Yep, spectrum A is compound Q. So that's the answer to that one. Spectrum A is compound Q. What about the next one? Well, the next one has 3 types of carbon. 2 of these 2 types of carbon are in the alkyl range. They're at about, what do you want to call that, 20 or 30 parts per million? And then there's another one at about 130 parts per million. That's a very typical range for vinylic carbons, carbons that are involved in a carbon-carbon double bond. So we're looking for a compound that is 3 types of carbon. One of those types of carbon is vinylic, and that has to be compound P. We already said compound P has 3 types of carbon. One of them is vinylic, and the other 2 types of carbon are alkyl. There's 2 of this type and that unique CH2 in between them. Interesting that 2 of the peaks are twice as high as the other one. You can't always make too much out of relative peak heights on carbon NMR. It's usually not very meaningful, but it is suggestive. And it just so happens that 2 of these 3 peaks are for carbons that are doubled up. There's 2 of each of them. And then there's just 1 of this other CH2. So spectrum B must be compound P. What about spectrum C? Well, spectrum C is 1 peak. That means there's only 1 kind of carbon in it. And we had only 1 structure that had only 1 kind of carbon, compound R. So that must be the answer for question C. And then for the last one, we have 4 peaks. It even says that explicitly, and what their chemical shifts are. We had a compound that had 4 different types of carbon other than the one we first encountered, and we said there's going to be a carbonyl, an aldehyde carbonyl. There it is at 203 parts per million. So spectrum D must be that 4-carbon aldehyde, compound T. You could call it butanal if you want. Al for the aldehyde functional group. We'll eventually get to naming aldehydes and ketones when we get to chapter 19. But that's basically it. So it looks like structure S doesn't show up and structure O doesn't show up. So those are the 4 answers for those 4 carbon NMR spectra. What about proton NMR? Well, we're going to approach this very similarly, except that we also need to pick structures that are consistent in peak integration. In other words, in the numbers of hydrogen atoms that are for each resonance, and also consistent in spin-spin multiplicity. That's a little more difficult since spin multiplicity isn't always as simple as we would like it to be. But we'll do our best. So what you want to do again is look for, in each case, a compound that has the correct number of carbons in the correct ratio. We've got a 1 hydrogen singlet and a 3 hydrogen singlet. That they're both singlets is very suggestive. It means there's no adjacent hydrogens for each of them. So we've got a 1 carbon resonance at about, let's call that 3.3, something like that, and a 3 hydrogen resonance at about 1.3. So they're in a ratio of 3 to 1. That means that doesn't necessarily mean that it's literally 3 H's and 1 H. All we know from the integrals is the ratios, the relative numbers of hydrogen. So they must be in a 3 to 1 ratio. Well, do we see any compounds with only 2 types of hydrogen? Well, let's see, this one certainly isn't, because there's 1 type of hydrogen here, 1 here, and 1 here. So that's not it. Compound Y has 1, 2, 3 types of hydrogen at least, so it's not that one. Compound Z looks at first blush like there's 1, 2, 3 types of hydrogen. Actually, compound Z will have 4 types of hydrogen because the 2 hydrogens on the vinylic CH2 are different from one another. One of them is cis to the ethoxymethyl group, the other one is trans to it. So it's certainly not compound Z. And we can eliminate compounds V and W because they will have aromatic hydrogens. They both have aromatic rings. Aromatic hydrogens are usually round and about 7 parts per million, maybe 7.5. And there's nothing nearly down that far. So it must be compound U, and compound U matches very well. Compound U has two types of hydrogen, one in the CH3. Those three are alpha to oxygen, and we would expect to be somewhere between 3 and 4. And then the 9 equivalent hydrogens in the tert-butyl group. Note well that the central carbon has no H's on it. It already has 4 bonds, so there's no H's there. So there's 9 in the tert-butyl group to 3 in the methyl group. 9 to 3 is 3 to 1. And so the 1H resonance is for the 3 H's in the OCH3 that we would expect to be further downfield because of the electronegative oxygen atom. And then the 9 equivalent hydrogens in the tert-butyl group are going to be the one with a 3 times larger integral at about 1.3. So the spectrum E must be compound U. What about the next one? This is significantly more complicated, isn't it? There's 1, 2, 3, 4, 5, 6 types of hydrogen. And not only that, but we can tell something both from the splitting and from the chemical shifts. First of all, these hydrogens out here at around 5 or 6 parts per million, that's typical of vinylic hydrogens. Those hydrogens that are directly attached to a C double bond C type carbon. Those are called vinylic hydrogens, VINYLIC. And we have a grand total of 3 of those. We also have a 3H triplet and a 2H quartet. And class will make that pretty clear. That's a clear signature of an ethyl group, CH3, CH2. The 3H resonance is the CH3 of the ethyl group. It's split into a triplet because of the 2 adjacent hydrogens. So 2 plus 1 equals 3. You take the number of adjacent hydrogens and you add 1. 2 plus 1 is 3. You will have 3 peaks in that resonance. Similarly, this quartet is the CH2 resonance. It's split into a quartet into 4 peaks because of the 3 adjacent hydrogens in the CH3. 3 adjacent hydrogens, 3 plus 1 is 4, 4 peaks. So we're looking for something with an ethyl group, and we're looking for something with 3 different types of vinylic hydrogens. And I see only one compound with vinylic hydrogens, which is compound Z, and also it has an ethyl group. So remember, you need to know ET means ethyl, CH2, CH3. That's one of the commonly used abbreviations that you will need to know, like PH for phenyl or BU for butyl. It's just a commonly used abbreviation. So how many types of hydrogen would this have? Well, there's 2 types in the ethyl group, CH2, CH3. The CH2 here is a 3rd type. This vinylic hydrogen is a 4th type. And then, as we mentioned earlier, the 2 vinylic hydrogens are different from one another. One is trans to the rest of the chain, the other is cis to it. They have different chemical environments. So there's 6 types of hydrogen. So spectrum F must be compound Z. It's the only one that has the requisite number of types of hydrogens. What about spectrum G? Well, here we have some peaks that are at a chemical shift even further downfield from the vinylic range. Before, our peaks were in the 5 to 6 parts per million area. Now we're at about 7.5 or 8. So those have to be aromatic hydrogens. In addition to that, we have again an ethyl group. We have a 3 hydrogen triplet for the CH3 and a 2 hydrogen quartet for the attached CH2. So there must be an ethyl group. So we're looking for something with an ethyl group and with an aromatic ring. And when we look at our structures, there's 2 compounds that have an ethyl group and an aromatic ring. So how do we know which it is? The way you know is by the chemical shifts. And in particular, if you're looking at the chemical shift of the CH2 in the ethyl group, that's here at about 3.5 parts per million. That's very far downfield shifted. We usually find that with hydrogens that are alpha to oxygen or halogen or something electronegative. So that must be a CH2O. Those H's must be alpha to an oxygen. If the oxygen were not there, then we would expect the CH2 to be much further upfield, at maybe 2 or something like that. Kind of like we saw in this spectrum, in spectrum F. Actually, no, spectrum F is not a good comparison. Spectrum F also has an oxygen next to the CH2. So if you had a compound like ethylbenzene, that would be a good spectrum to look up. I expect you'd see that CH2 at more like 2.5 or something like that. But being this far downfield, look at that, it's like 4.3. The CH2 must be attached to the O, must be attached to the oxygen. And so that has to be compound V. In compound W, the CH2 is attached to the carbonyl carbon. And that would pull it downfield a little bit, down to maybe about 2.5 parts per million, but not nearly as dramatically as the electronegative oxygen does in compound V. So I would expect spectrum G is going to be for compound V. Let's see how we're doing. Yep, looks good so far. And we said that spectrum F was for compound Z. So spectrum G is for compound V. Finally, we have spectrum H. And so we have 3 types of hydrogen here. We have a 6H doublet, a 1H septet, and a 2H singlet. So that 2H resonance has no hydrogens adjacent to it. So there's only 3 types of hydrogen. That pretty much narrows it down for us. Because that tells us immediately it can't be compound W, because then we'd have aromatic hydrogens. There's no aromatic hydrogens here. The most downfield peak is at about 3.2. So we're looking for something with 3 types of hydrogen that are in a 2:1:6 ratio. And usually when you have a 6H doublet and a 1H septet, I'm sure we will see an example of this in class, that's indicative of an isopropyl group, like in compound X. Here you have 6 equivalent hydrogens that have 1 adjacent hydrogen. So that 1 adjacent hydrogen, 1 plus 1 is 2, splits the 6H resonance into 2 peaks, a doublet. And likewise, this CH over here has 6 adjacent hydrogens. So 6 plus 1 is 7. We would expect that CH hydrogen to be split into 7 peaks, a septet. And then finally, we have this CH2 that is no adjacent hydrogens. This carbon has no H's on it. That carbon has no H's on it. So that CH2 would be a singlet. So that last spectrum, spectrum H, has to be compound X, has to be that isopropyl ketone. And again, I've given some hints as to where to start. Let's see which one. In fact, I started with spectrum H, which probably wasn't the easiest one to start with. But this gives you hints with solving a spectroscopy problem like this as to where to start, what you should look at first. There's some hints here right on the worksheet. And then finally, we have a combination spectroscopy problem. And so we're given a carbon NMR with depth data. It says all of these carbons are CH2 type. We've got a proton NMR spectrum that really only shows 1 clear multiplet, doesn't it? This 2H triplet over there at about 3.5 parts per million. We've got an IR spectrum, which again, one of the peaks in the IR spectrum really stands out and tells us what kind of functional group we should be looking for. And then we've got a mass spectrum where I've pointed out the molecular ion. It's a little hard to see, but it's down in there. So from the molecular ion, we recall that means that the molecular weight of this compound is 118. And so in class, we'll go over a step-by-step method that you should use for solving combination spectroscopy problems. The first thing you want to go after is the molecular weight, and from the molecular weight, try to get a reasonable formula. And I've basically taken you through this already on the worksheet. So look at the mass spectrum and find the molecular ion. We've done that. So that must be the molecular weight of the compound, 118 grams per mole. And I even tell you here, write this down. So there is a possibility for partial credit on this question. Once we know the molecular weight, it's important to understand that given the molecular weight, your choices of molecular formula are not infinite. There's only certain possibilities given that molecular formula. We know, for instance, that there has to be fewer than 10 carbons because, and I pointed this out here, because 10 carbons would weigh 120 parts per million just by themselves. That's over our molecular weight. There's no room for hydrogens or oxygens. Another thing we'll be pointing out in class is that the two formulas you want to try first are, I'll write this over here so you can see them, are CXHYO and CXHYO2. Why is it not working? And this is in the class notes and something we'll go over in class. These are reasonable formulas for you to try. Formulas of these types, CXHYO and CXHYO2. Another really good formula to bear in mind is CN H2N plus 2. What that means is that if there's N carbon atoms in the molecule, there can be no more than 2N plus 2 hydrogens. That's one of the rules about molecular formulas that you would have learned about in chapter 7 when you talked about a degree of unsaturation or index of hydrogen deficiency. So if there's N carbons, you can't have any more than 2N plus 2 hydrogens. There's a limit on the types of formulas you can have. It's not absolutely limitless. There's certain restrictions on what the molecular formula has to be. So we know everything needs to add up to 118. And I show here in the hints as to where to start. So we said there cannot be 10 carbons. That's greater than the molecular weight. If there were only 9 carbons, then the formula would have to be C9H10. And I'm having a real hard time coming up with a formula that would be that unsaturated. It is 5 degrees of unsaturation, and you would need a benzene ring in order to do that. And if there were a benzene ring, we would first of all see aromatic overtone bands in the IR. There are none. If there were an aromatic ring, we'd see aromatic hydrogens. There are none. They'd be at about 7.5 parts per million. We only go down to about 3.6. We would also see aromatic carbons. They're at about 120, 130 parts per million. There are none. We top out at 60 something. So there's no aromatic ring. So it can't be C9H10. So we'll keep going. We also already, by the way, know that there's an alcohol from this OH stretch in the IR spectrum. We also know a couple other things. We know there's no carbonyl, no C double bond O. I don't see that big peak at about 1700 wave numbers. We also know that all of our CH stretches are just below 3000 wave numbers. So I don't expect any of those H's to be attached to sp2 hybridized carbons. We're looking at essentially a saturated compound, no carbon-carbon multiple bonds. And that's consistent with our NMR spectra as well. So we're still trying molecular formulas. One possibility that adds up to 118 is C8H6O. That still seems, it's too unsaturated. How are you going to have only 6 hydrogens with 8 carbons? It's hard to come up with anything. What if instead of 8 carbons, we had 7 carbons? See, this is what you should do on the exam. You have to keep trying things. Your first try may not work. You got to keep going. So what if there instead, we already tried 10 carbons. That doesn't work. We tried 9. That doesn't work. We tried 8. That doesn't work. Let's try 7 carbons. The formula would have to be C7H18O. That's impossible because 18 is more than the 2n plus 2 rule allows for. 2 times 7 is 14, plus 2 is 16. With 7 carbons, the most hydrogens you can have is 16. 18 is too many. You can't fit 18 hydrogens on. So it looks like we're running out of options with just one oxygen. What if instead of trying 7 carbons and 1 oxygen, we tried 6 carbons and 2 oxygens? We would wind up with C6H14O2. That adds up to 118. 6 times 12 for the 6 carbons is 72, plus 14 for the 14 hydrogens is 86, plus 32 for the 2 oxygens is 118. So that adds up to the required molecular weight. So it looks like it's a saturated compound with 2 oxygens. Write this down if you get to that point in the exam. We have a reasonable molecular formula that at first glance matches the NMR spectra, certainly leaves it open for an alcohol in the IR spectrum, and is saturated, which makes sense since we're not expecting any aromatic or vinylic carbons. So we need to come up with a reasonable formula or a reasonable structure for C6H14O2. Now let's look at what else we have. We have the carbon NMR and the proton NMR. We have the depth data for the carbon NMR, which says we have only 3 types of carbon and they're all CH2s. So how can we have all CH2s? It means there's no CH3s, no CHs, and no quaternary carbons. We also have to allow for an OH group since we have clearly an alcohol per the IR spectrum. And so we need to have some way to have 6 carbons in total in the formula. Remember, our formula is C6H14O2. So that's our formula. We have 6 carbons total, but there's only 3 peaks in the carbon NMR spectrum. So that means we have to have some kind of plane of symmetry to this molecule. There's 6 carbons, but there's only 3 types. And we also have an OH to deal with. So we have to have 3 types of CH2s and an OH. And what I would recommend you do is that you write that down. So write down CH2. There's one CH2, and we have 3 of these. There's one, there's another, and there's another. We have 3 CH2s, and we know that we have an OH. And we somehow have to have a plane of symmetry. So that means each of these CH2s, there has to be 2 of them. They're doubled up. So we don't have just 3 CH2s. We have 6 CH2s. The way I know that is because there's only 3 peaks on the carbon NMR. But there's a total of 6 carbons in the formula. So there have to be a total of 6 CH2s. We know there's an OH from the IR spectrum. Let's add all that up and see what we have. We have C6, H24681012, 13, O. So we're accounting for C6H13O. Go ahead and write that down. we've accounted for C6H13O. That's how much we've accounted for. And one skill that you need to have, something that you need to know, is to be ready to make subtractions. That's very helpful when trying to solve any kind of spectral data. And if we subtract C6H, oh, it won't let me do that. Let's try again. It may still want to add the H. Okay, good. C6H13O. So we'll subtract C6H13O from C6H14O2, and you'll see that what you have left is HO. When you subtract C6H13O, which is what we've accounted for, from C6H14O2, which is our formula, what's left is another OH group. So that means we don't have just one OH group, we have two OH groups that are equivalent. And we haven't even looked at the proton NMR yet. But look how much information we've gotten even without looking at the proton NMR. So all we need to do now is connect all these pieces together. That's a really vital skill that you will need to know. You will need to have that skill in order to solve these problems, which is putting pieces together. You need to write down pieces and then put them together to make a logical structure. That's something you'll need to do to solve a lot of these active questions as well. So we have 6 CH2s and 2 OHs. I can think of only one way to do that. Just line up all 6 CH2s. The OHs have to go on the end because oxygen can only have 2 bonds. And so you have this structure, 1,6-hexane diol. And the question doesn't say to name it, but that is the name. So that, I think, is the most reasonable structure that's consistent with all the data. Just for fun, let's look at the proton NMR spectrum. Looks to me, now I'm beginning to question myself. No, I think we're good. The proton NMR spectrum has only 4 types of hydrogen in a 1:2 to 2:2 ratio. The 2H triplet that's pretty far downfield has to be the 2 CH2s that are right next to the oxygen. That will pull these 2 CH2s very far downfield to about, usually it's between 3 and 4, and that's right there at 3.5 parts per million. The broad 1H resonance is going to be the 2 OH groups. So it's 1:2 to 2:2. It's really 2 to 4 to 4 to 4. And that adds up to our total of 14. And the remaining CH2 resonances are really ugly, and we don't see any clear splitting there. That's because you've got full freedom of rotation around all of those bonds, and you just get very complicated splitting. It's not nice, neat splitting like this triplet over here. That's split into a triplet by the adjacent CH2s. By the way, notice that we get a triplet, which means that the hydrogen on the OH group doesn't split the CH2. That's pretty common for OH hydrogens. They very often do not split adjacent hydrogens. And the reason is that OH hydrogens undergo very rapid physical exchange. In other words, you have hydrogens hopping off of one oxygen onto an oxygen in another molecule, and they're exchanging H's very rapidly on the NMR time scale. So that prevents the splitting from occurring. So as I said, I've given you all these hints on where to start on a combination spectroscopy problem. You also have the step-by-step method that's given in the chapter 13 notes. So that's how I would approach a question like this. And I've given, again, all of the answers. So that's about it. So much for chapter 13. Chapter 14 we will cover, but much later in the term. So after chapter 13, the next chapter we'll cover is chapter 15. And that won't be for quite a while as I speak. So once again, have a good weekend. And I will see you all on Wednesday.